Hello, my friends. This is Dr. Mohamed Nezami again with another one of my presentations on RF and microwave circuit and device design and 3D model. I'm an independent contractor. I do design contracts. If you have any product, any boards that you need to design, active, passive, anywhere from DC to 35 gigahertz, please let me know. Contact me on this number on these apps or email me. And then we can go further. I have very reasonable rates as opposed to rates that are commonly used in the United States and Europe. I take your design and work with you on the specifications, on documentation, system implementation, system simulations and verifications, and turn that into an actual circuit design. Do design and modeling using HFSS, ADS, RF Pro, Momentum, and then draw schematics in Altium and Cadence Allegro, do BCB layout, turn in board, Gerber files, bill of material, all of that I can do for you with a group of people that also come in to help sometimes if I need expertise like microcontroller designs and firmware coding. Okay, so today I'm going to continue one more presentation on radial power combiners. Okay, and of course, last 3 sessions, I have presented few classes, different designs of these devices. Now we know that radial power combiners and splitters are mainly used for a lot of times in high power splitting and combining. That is in power amplifier designs, for especially for like GaN-based power amplifiers. They're used for places where you need some kind of cylindrical form factor to design, such as ground stations, SATCOM, transponders, and phased array antennas, antennas that have specialized coverage where you need to like cover sectorial or octagonal or hexadecimal different beam switching viewers. So today I'm going to present an interesting design in here, and this is next session I'm going to present. Well, next 2 sessions will be 2 more radial combiners, and then we'll be done. We'll move on to something else. But today's presentation is on this device here, and this is a very interesting combiner that is based on an oversized coaxial line. So basically what you see in here, this is my own way of implementing a coaxial connector. This is just a cab, and just to close the so I can excite a wave into the inside of this cavity here. What this cavity is, it's a coaxial cavity basically, because what we have here is a center conductor, and the center conductor and the outer conductor is this green one here. And then we have the peripheral ports along the sides. This is 8-way combiner or 8-way splitter, whatever you want. And it's implemented using microstrip lines. We have a microstrip line, 50 ohm line, and then we have the probes that are extending quarter wavelength into the coaxial cavity. Okay, so let's go through this, and just so that we can start ahead of time, just to show you, this is the design in the HFSS. Okay, basically what we have this here is Teflon material surrounding the as an insulator for this small piece of coaxial line, okay, and then we transition into air-filled cavity, a coaxial cavity, where at first we start out with a little suction in here with air, and then we go in and start coning or tapering, okay, you might say, toward the load, and the load is here, all these 8 in parallel. So that's this point here is a very low impedance. As you can see, it's 50 divided by 8, okay, as opposed to 50 ohm on this side. So what we have in here, this is a tapered inner connector and outer connector that tapers so that it matches the impedance from 50 to the parallel combination of these probes that are surrounding here. And so let's see, if you look at the this is the inner coaxial of the inner, the coaxial section, of course, we extend it so that the radius of this here, the radius of this here has to be, we pick the diameter so that it can fit all of these probes in here. So if we need to go 16, 32, 64, whatever, we just keep going, extending the radius or the diameter of this cavity, okay? All right, so let's get back to the lecture. Just as a reminder, like I told you always, all of these designs, you can purchase the design file in HFSS, archived HFSS for the price showed on here. This money goes toward, I donate it, I don't use it myself. Okay, the other announcement I have right now is, if you like what you see here being presented, and if you're in the, I'm in the Middle East, in Jordan. I have many years experience in the United States, and I'm almost retired back to Jordan. So I'm going to be holding a 3-day training session, okay, hands-on training, and it will be held in February 15 to 18, 2023, coming year, at the Olive Branch Hotel that is here in Jordan, in Jerash City, my hometown. And the price is basically $1,000. That will include the hotel room and the meals. So you get 3 days of accommodation and meals, and also some nearby trips after the training as well. So there'll be this session. The first session is on the RF and microwave device designs, the stuff that you see on here in my presentations. We will do hands-on, start design it from scratch. I'll walk you through it so you get really good at 3D modeling and designing. I will follow up with that right after that. There are a few more training sessions that involves signal integrity using HFSS and ADS. I will also have a session that includes cadence, schematic PCB designs as well. Okay, so if you think you can make it for this date, please let me know so I can get you registered. And I'm very sure it's worth it. The price is very reasonable to the people around here, especially in the academia in Saudi Arabia, United Arab Emirates, Egypt, Turkey. This is really reasonable because this training here is many more dollars in the United States, and you have to travel very far and so on. So you can have this training right here at home, here and next to you. You can fly in or drive into this, and you'll have a great time. So let's get back, just refresh your memory. We're doing, this series is on Radial. This playlist that you see here, you can click and go through the other videos that I have right now. It is on Radial combiners and splitters. And we know that we have 2 ways to go when we have to split the signal into N paths, like we do in antenna arrays, beamforming antennas or power amplifiers. We can go multi-steps using corbett structures like Wilkinson's, or we can go in-way combiners and splitters using radial methods, okay? And those are basically, we could all either have cavity combiners like we did, we covered this last time, and last time we have sessions on these. And so today, I forgot to mention that today it's, this yellow should be here. Today we're doing this, the conical transmission line combiner. This is a non-cavity, of course, non-resonating cavity, okay? And then we have spatial combiners that we will talk about. So why do we do this versus this? Why would you go to the extent of designing a signal splitter or combiner that is cylindrical in shape and it's got metals and things like that into it? And we have covered these last time, we mentioned them, but today I'm gonna give you another deeper look at why, really. It's not just the fact that in the corbett structures, they're done in planar forms, strip lines, microstrip lines, or their variants, and those usually have lots of loss. There's lots of mismatches, temperature dependency on the substrate. They can't handle a lot of power like the ones we're covering here handles a lot of power. They're narrow banded because they're based on a quarter wavelength sections. And I'll show you in a minute what we mean by that, because obviously any, whether it's Wilkinson or hybrid 90-degree splitter or what is it, the rat race, the circular quadrature splitter, all of these are based on resonant lambda/4 type devices. So, so again, if you have a power amplifier, we did mention this last time, in the conventional methods, we have a split suction and a combined suction. So we get a signal, we have to split it in ways to get to the N amplifiers, and then we have to combine in ways to get to a common output to drive to the antenna, okay? So unlike that, the radial combiners and splitters or spatial combiners, they do it instantly without immediately, they do that. So without any transitioning, and that is of course of benefit. Let's just go a little bit deeper into this. So why would I use radial combiners like the one I'm just about to show, or the ones that we have shown already, when you can do, for instance, 2, 4, 6, 8, when you can do an 8-way splitter like this, for instance, you could design this and you could design it into many sections, you know, like in this case, 3 sections, so that you can offer wider bandwidth, okay? And the reason is because if you look at all of these devices, okay, the rat race, the hybrid or the Wilkinson, all of those are based on a 90-degree suction, okay? And that suction in here, that's what transforms the impedances between the output and input. Same way here, same way here. And so if you look at the, so while you're doing this, if you look at this now, when you look at the design of if you ever designed one of these multi-stage Wilkinson divider or combiner, you can see that you start out with the sections. Start out on the right-hand side from the load. You have low impedance, and then the lines keeps narrower and narrower and narrower. That is to get, meaning higher and higher transmission line impedances. And as you know, eventually beyond, you get to a point, and you can see that on the BCB example that I have here, eventually you get to a point where you almost have to lay out a hair width line to get to as your first stage. So, and then you can't, beyond that, you can't. You get to a point where the lines, for instance, can be less than 5 mils, and you can't fab 5 mils with this stuff. So, and it becomes very lossy as well. So that's one of the reasons. And let's just take a quick look at this app here. This is a calculator for a multi-stage Watson divider. So we have an input in here, two outputs, two-way divider, okay, and multi-sections. Okay, we start out, Z1 is here, 2 is here, and all the way to N is here. So right now I have it set to just one section. And you can see with one section, of course, we always get the impedance lines in here are right here, this value, which is 70.7 ohm, okay? Now, this is very narrow band, as you can see in here. If we want to go a wider band, we start adding sections. And by adding sections, we widen the bandwidth, and you can see that the lines in here, this column here gives you the suction impedances. These are the impedances in here. And this is the isolation resistor values. Okay, those we have no problem with. But look at the impedance lines. We start out on this side. The first line is 57, and then 70 ohm, and then 87 with just 3 sections. So if we go to 6 sections now, look what happened now. We have much wider bandwidth, but as you can see, the lines are starting to get to near 100 ohm. That last line here is 100 ohm, and that you can figure using Duroid with, like, say, 15 mil Duroid, that's probably somewhere between 7 to 10 mils, which is very narrow, if not narrower than that. I can calculate it later. I should have done that. So let's go to 8, and you can see that the impedance becomes very very large, okay? So that's one of the essential differences why we would not want to use this method, other than the fact that we cannot handle high power and so forth. So okay, so now, having said that, also want to refresh your mind that what we're doing basically in the case of power amplifiers is that we are designing a radial splitter on one side and a radial combiner on the other side. And then we have cards that can be fitted into the cavity in here, the air gap between the inner and outer conductor. This, of course, this is a coaxial connector. What happens to this coaxial connector is you have 50 ohm in here. We start out with SMA or N-type connector, and then your inner connector and outer connector diverges or tapers out to the point where it can match and physically becomes large so that you can fit circuit boards inside of it. Okay, so that's basically how the radial combiner that I'm going to show you today, where it would be applied for. Okay, and here is another diagram I took out of the IEEE on one of the designs. So start out with an SMA connector in here. You take the inner connector and you taper out, okay, to match to a specific impedance, and then you can keep the impedance after that uniform along the line in here, and then you stick in probes to pick up the signals on here. So when you look at these devices, they're basically now made of the following sections. Okay, the first section is a microstrip probes located on the same planar substrate, and that's these guys here. And I'll show you in a minute the design that I have done as a demo for this presentation. And then an oversized coaxial waveguide with a short wall. Oh, I forgot to mention the short wall is this piece here, okay? This piece here, beyond, you have your probe in here, and beyond your probe, you want to make sure that the probe sees open impedance. So what we have a quarter wavelength. We extend the inner and the outer, a quarter wave, and then short it, okay? What that means, at this point here, where you pick up the signal in the radial dimension to pick up using the probes, all the probes are going to see as if this is really open, and all the signal will go into the probe and will not propagate toward the shorted end. And then you have a central standard coaxial connector to the overside. That is this connector. Okay, that's your starting point. Okay, so today's design, the one I'm going to show, basically is exactly the same. So what we have, we start out with a coaxial line in here, coaxial connector, okay, that has Teflon inner and outer shield. And then we extend that a little bit, and then we taper. We have a tapered line transformer that transforms impedance from 50 to all these parallel combination impedances in here, okay? And then we have a little cavity in here where you place the probes in here are placed, okay, around. These are 8 of them. And there's openings, and these openings are to let the signal go in without any disturbance to the signal, okay? And as a design rule of thumb, the width of this line in here, usually it's about a quarter wavelength of the waveguide, okay? And then the height is also 1/2 of that. So this is a rectangular that is quarter wavelength width, length, and then the width is 1/2 of that, okay? And then you have a strip line board in here. Now this strip line board, of course, you don't stick individual probes. This is all one substrate, one tray of probes. And then this here is 2 pieces basically, come in, 1 piece on top, 1 piece on bottom, and you screw it together with the substrate sandwiched between them, okay? Let's see what else. The name of this, the way that we design these taper transitions or taper transformers, sometimes we have many forms. We have Chebyshev, we have other maximally flat with minimum ripple and so forth, just like a filter. But there's one class that is called Klopfenstein transformer, and this gentleman here came up with one where it exponentially varies the diameter of this to get to from this point to that point, okay? And those are documented in there. Of course, the impedance of this line in here is this formula here, which is the coaxial impedance formula, which is 60 times the natural log of the outer to the inner diameter, okay? So the ratio, as you can see. All right, so what else we have here? We've covered this. This is a quarter wavelength from the center. And so we have the, okay. One thing to mention in here, there is a taper section other than this section that starts here and ends here. There's also another small section in here, discontinuity, where that you start out tapering the outer, but the inner is constant, okay? So that's just a transition, and it's part of that. So let's look at the board. The board basically is this. So we got the probes in here are all quarter wavelength from this point. This is a 50 ohm line, okay? And the probes are capped, just like we do with metallic. And this is one of the examples that I will do next week, is coaxial capped, inner capped probe. And in that case, the probes are in this alongside the wave propagation direction, unlike this where it's orthogonal, okay? That one is better because you keep going in the same direction. You can build your boards. This one here, you go out here, you could feed antennas that can be used to like hemispheric coverage antenna, or you can go to power amplifiers. But in that case, the power amplifiers have to eventually, you have to mechanically have a 90-degree transition from here to boards that are going in along the Z direction, okay? So let's look at the design that we have. So we have this, started out with this. The excitation, so we can see that this is the first excitation is this here, which is that or there, that cap has put in a wave port on the inside so that you're actually driving this thing. And then the other ones are basically these probes with the 50 ohm lines. Okay, that's these guys. So we drive these with a lump port in here. Okay. So I run this, and let's see what else we need to cover. The board that is used is a Duroid 6002. In this one, let's look at the frequency response of this. This was designed, and you can see here that, let me see, to put a marker. So let's put some markers. This is between almost 10 gigahertz and 20 gigahertz, you can see. And it's not fully optimal right now because we do have a rebel on there. So that's caused by the mismatch from the probes. The probes are still needs further optimization. Okay, so let's look back at the device itself. And let's look at the E field and how the signal propagates. Okay, so signal comes in here, as you can see, it propagates through multi-mediums. The first medium is the Teflon filled coaxial line piece, which is the connector. And then you go through a coaxial air-filled medium all the way until you get to the probes, where and the probes, of course, the signal radiated inside the cavity will get picked up by the probes and will propagate to these lines. So let's go ahead and animate this. Okay, here we go. So you're seeing how the signal is fed here. This is a divider right now. It's not a combiner. We'll put a combiner in a minute, show how that works. Okay, so let's look at the sideways and show you how the quarter wave distance. This is a quarter wave from this point onward. That's quarter wave. So you can see that the signal is being loaded with an open, very high impedance and reflecting back to go back to the probes. So you can see how these are the probes picking up the signals, feeding it to the 50 ohm terminal. Okay. Now, if you need to make it into a combiner, you can do that easily by going in here to fields and edit sources. So we can put this 0 right now and then excite all of the peripheral ports with signal, with waves. Okay. And it's going to recalculate. All right, here we go. So right now the signal is going in every port. And oh, this one I left out. So let's go back and put a signal on that guy there. There's one that should be 0 right now. Ah, 2 of them are dead. Okay, so let's go. I knew there's a missing part because this is the beauty of this device is that it's symmetrical. So what you should see is exactly all the way around 360 degrees. And that's the beauty of this is that the in-way splits are all they have the same characteristics in terms of phase and magnitude and delay. So, and there's little that varies. There's no mismatches on this unless you have mechanical mismatches manufacturing, which can't be happen if you keep this board as a separate, as a complete board, and you sandwich between these two, there's not much that you can mismatch in terms of manufacturing on this. You can see that all the signals are going up to here. All right. So now we covered this and covered this. Okay, so let's talk about how you would utilize this into a power amplifier device. Okay, so here is a how you would utilize it. Basically, we have to have two of those because in power amplifiers, as you know, one will be a splitter, one will be a combiner. So let's, if you talk about a GaN amplifier array, you have 8 channels. Each one has a separate amplifier. And then you feed, basically you bring in a common signal, you split it, and you feed it into every individual amplifier, okay? And on the other side, you would do the same. And of course, physically, it would look like this. I took this out of the open literature. And you can see here, this is one combiner, and this is one splitter. And then these here are basically all your amplifiers encapsulated into this assembly. Okay, so now here is for this one here, this is actually one implementation that I found, which you can see what the pieces are. Okay, here's the tray that has the board on it and the connectors, or 8 connectors. The feed lines, 50 ohm lines, they go in, and you can look at this, it's the cap is lifted. And then you have the probes placed on the inside. And then you have the, of course, this here is the inner conductor with a screw here that is to screw in the N or SMA inner connector. And this is the cap, basically is the outer shield of the coaxial line cavity. And so here's SMA, that's the cap top, and that's this, and beneath it is the suction. There is a quarter wavelength distance. Another example that I will be covering next week is this device here. Now, this is an interesting one where instead of picking things orthogonally to this, we do the probes, we place them on the bottom through a ring cavity on the inside. But it's essentially still the same as we just covered. And this is one implementation that I found in the open literature where you have the splitter on here, the combiner in here, and these are just feed through lines. So what they're doing in here, they're testing this back to back to see how their performance. So there are no amplifiers. But in real life, all of these sections in here will be having amplifiers. And the neat thing about these is modular. So anytime one would burn, all you have to do is just pull one out and just stick it in. And there's also you can see, I think they call it the grace factor, is where you can actually compute what happens when one amplifier fails, as opposed to having all of them operated, and you can see how much degradation in output power you can get. Okay. Another copies of some implementations that I've seen online posted. Here's one where they opened the one of those, and you can see the boards are right here. You see those boards, how they're radially placed on the inner connector, the conical, the oversized inner connector, inner conductor of the coaxial line. This is another one right here also. You can see the southwest 2.9 millimeter connectors on here. Another one that is done also. Oops, what happened? Okay. This is another design that is done, and I think this is like L-band because you can tell it's pretty large. Okay, so these are 8-way splitters. This is the inner conductor, and that's the shield right here. And of course, the extension below that is a quarter wavelength. And they made this, of course, as you can see, you come in here and go in. Okay. So my friends, this comes to an end on this one. Next week, I will be showing 2 more variants of the radial combiners. I thank you for your watching this. Please share the video and click like if you like. Okay. All right. Thank you. Have a great day or night, wherever time it is where you are.